Bismillah ar-Rahman ar-Rahim. K is a positive integer. We have sum n from k plus 1 to infinity minus 1 to the n divided by n choose k plus 1 plus sum n from 1 to k 1 over n times 2 to the n. This sum is multiplied by 2 to the k times minus 1 to the k plus 1 times k plus 1. Let's focus on this part here. The binomial coefficient is n factorial over k plus 1 factorial, n minus k minus 1 factorial. Both factorials go upstairs. We can take k plus 1 factorial outside the sum. N minus k minus 1 factorial over n factorial. This is equal to 1 over n times n minus 1 all the way to n minus k. We can write this ratio as product m from 0 to big K of 1 over n minus m. We do partial fractions to this product, converting it into sum m from 0 to k, gamma m over n minus m. Gamma m is this product without n minus m. Then we replace n by m. Gamma m is the product j from 0 to m minus 1, 1 over m minus j. This product takes care of these brackets here. There is also another product, j from m plus 1 to k, 1 over m minus j, to take care of these brackets. The first product here is 1 over m times m minus 1 all the way to 1. This is 1 over m factorial. The second product has k minus m terms. We multiply each term by minus 1. So we have minus 1 to the k minus m. Then the product j from m plus 1 to k 1 over jm. This is 1 over 1 times 2 times 3 all the way to k minus m. This product is equal to 1 over k minus m factorial. Gamma m is minus 1 to the k minus m divided by m factorial times k minus m factorial. Interchanging the order of summation, this sum here is k plus 1 factorial, sum m from 0 to k, gamma m, sum n from k plus 1 to infinity, minus 1 to the n over n minus m. Change n to n plus m. Now the lower limit of sum becomes k plus 1 minus m. N minus m becomes n. This n becomes n plus m. From this summation here, separate the term corresponding to small m equal to big K. So we have this quantity here, the sum stopping at k minus 1 plus k plus 1 factorial, gamma k, summation n from 1 to infinity, minus 1 to the n plus k over n. We can take minus 1 to the k outside. This sum is minus log 2. We know that log 1 plus z is summation n from 1 to infinity, minus 1 to the n minus 1 over n, z to the power n. So what we have here is minus log 1 plus 1, which is minus log 2. Gamma k is equal to minus 1 to the 0, 1 over k factorial, 1 over 0 factorial. Gamma k is 1 over k factorial. This product here is equal to k plus 1. This part is equal to minus 1 to the k plus 1, because we have this minus sign, and minus 1 to the k, times k plus 1 times log 2. This sum here is written with gamma m replaced by minus 1 to the k minus m over m factorial, k minus m factorial. K plus 1 factorial is k plus 1 times k factorial. K factorial times this product is k choose m. We have minus 1 to the k minus m here, minus 1 to the n plus m there. So this is minus 1 to the k plus n. Minus 1 to the k can be taken outside the sum, and here is minus 1 to the n. Write down the inner sum as summation n from 1 to infinity, minus 1 to the n over n, minus summation n from 1 to k minus m of minus 1 to the n over n. This first sum is minus log 2. From this part, we have minus 1 to the k plus 1 times k plus 1 times log 2. Then we have this summation. If this summation extends all the way to k, then we have 2 to the power k, because this is 1 plus 1 to the power k. This summation here is 2 to the power k minus 1. This one is k choose k. We can use this term to cancel the minus 1. We still have minus 1 to the k plus 1 to take care of this minus 1 to the k and this minus sign. K plus 1 summation m from 0 to k minus 1, k choose m, summation n from 1 to k minus m, minus 1 to the n over n. In this summation, we have n less than or equal to k minus m, which means that small m is less than or equal to k minus n. We can interchange the order of summation and write this double sum as summation n from 1 to k, summation m from 0 to k minus n. The summand is minus 1 to the n over n, k choose m. Our sum of interest is this quantity here plus this part. We combine this part and that part as minus 1 to the k plus 1, then summation n from 1 to k, 1 over n, which is here and there. Inside this bracket, we have 2 to the k minus n plus minus 1 to the n, sum m from 0 to k minus n, k choose m. we can show that this quantity of interest is exactly equal to this part because this sum is equal to 0 for every positive integer k. 1 plus z to the L is summation n from 0 to L. L choose n, z to the n. If we subtract z to the L, we get summation n from 0 to L minus 1, L choose n, z to the n. Now replace n by n minus 1. We get summation n from 1 to L, L choose n minus 1, z to the n minus 1. We need another result related to this sum, n from 1 to L minus 1 to the n over n, L choose n minus 1. We can write 1 over n as integral x from 0 to 1 of x to the n minus 1. Swapping summation and integration, we have minus integral x from 0 to 1, summation n from 1 to L minus 1 to the n minus 1, L choose n minus 1, x to the n minus 1. This sum is n from 1 to L, L choose n minus 1, minus x to the n minus 1. This is exactly the first result with z replaced by minus x. This sum here is minus integral x from 0 to 1, 1 minus x to the L minus x to the L. Carrying out the integration, we find that this sum is minus 1 over L plus 1 times 1 plus minus 1 to the L plus 1. Our main interest is to show that for every positive integer k, this summation is equal to 0. If k is equal to 1, then we have one term in the sum. Small n is equal to 1. What we have here is 1, 2 to the 0, which is 1. Then we have minus 1. M is equal to 0, so this binomial coefficient is equal to 1. We get 0. Suppose that for some positive integer L, this relation is true. To complete the proof by induction, we need to show that this summation with L replaced by L plus 1 is also equal to 0. So we write down this summation. Every L is replaced by L plus 1. Let's first separate the term corresponding to small n equal to L plus 1. This is 1 over L plus 1, 2 to the 0, which is 1. When n is equal to L plus 1, n is equal to 0. This binomial coefficient is equal to 1. This part is minus 1 to the L plus 1. Now the sum is from n equal to 1 to L. In the sum with respect to m, separate the term corresponding to m equal to 0. L plus 1, it choose 0 is 1. This term is minus 1 to the n. We get a sum m from 1 to L plus 1 minus n. We can also use the recurrence relation for binomial coefficients to write down L plus 1 choose m as L choose m plus L choose m minus 1. Split this sum into two sums. In this sum, replace m by m plus 1. We get a sum m from 0 to L minus n, L choose m. The sum is multiplied by minus 1 to the n. In this summation here, stop at L minus n. We need to add the binomial coefficient L choose L plus 1 minus n. If we start the sum at m equal to 0, then we need to subtract 1. These three terms are multiplied by minus 1 to the power n. We get minus 1 to the power n, which goes away with this term. This binomial coefficient is here multiplied by minus 1 to the power n. This sum times minus 1 to the power n is exactly like this term. So we can multiply by 2. We can also write this 2 to the 1 plus L minus n as 2 times 2 to the L minus n. Take this 2 and that 2 outside. We have a sum n from 1 to L, 2 to the L minus n plus minus 1 to the n times the sum m from 0 to L minus n, L choose m. And this summation is 0 by the induction assumption. What is left is summation n from 1 to L, 1 over n, minus 1 to the n, L choose L plus 1 minus n, which is equal to L choose n minus 1. This sum, by our previous result, is minus 1 over L plus 1, 1 plus minus 1 to the L plus 1. Together with this term, we get 0. Our sum of interest is equal to this term, plus minus 1 to the k plus 1 times k plus 1 times this sum, which is equal to 0 for every positive integer k. The quantity of interest is minus 1 to the k plus 1, 2 to the k log 2. The second sum is r from 1 to 2n minus 1, n is a positive integer, r times minus 1 to the r minus 1 over 2n choose r, beta of a and b is integral t from 0 to 1, t to the a minus 1 times 1 minus t to the b minus 1. Beta of a and b is gamma of a times gamma of b over gamma of the sum. A and b are positive integers. This ratio is a minus 1 factorial times b minus 1 factorial over a plus b minus 1 factorial. We can write this as a plus b minus 1 times a plus b minus 2 factorial. This factorial, together with these two, give us this binomial coefficient in the denominator, a plus b minus 2, choose a minus 1. Multiplying both sides by a plus b minus 1, we get that 1 over this binomial coefficient is a plus b minus 1 times beta of a and b. This exercise is for the purpose of expressing this binomial coefficient in terms of the beta function. We have 1 over 2n choose r. We set a plus b minus 2 equal to 2n and a minus 1 equal to r. This means that a is r plus 1, a plus b is 2n plus 2. So b is 2n plus 2 minus a. That's 2n plus 1 minus r. 1 over this binomial coefficient can be written as a plus b minus 1, which is 2n plus 1, beta of r plus 1 and 2n plus 1 minus r. We can make use of another integral representation of the beta function. Beta of z1 and z2 is integral t from 0 to infinity, t to the z1 minus 1 over 1 plus t to the power of the sum z1 plus z2. Applying this here, 1 over 2n choose r is 2n plus 1 integral t from 0 to infinity, t to the r divided by 1 plus t to the power 2n plus 2. Here is the sum of interest. After changing the order of integration and summation, the summand is r times minus t to the r minus 1. Outside the summation, we have t, because we originally have t to the r, divided by 1 plus t to the power 2n plus 2. What is the summation? R from 1 to m, r times z to the r minus 1. We can start from this finite geometric series. To obtain this sum, we differentiate both sides with respect to z. So this summation is the derivative of this function of z. We get this result here. Our sum is this quantity with z replaced by minus t and m replaced by 2n minus 1. Summation r from 1 to 2n minus 1, r times minus t to the r minus 1 is 2n minus 1 t to the 2n plus 2n t to the 2n minus 1 plus 1. Downstairs we have 1 plus t squared. If we multiply this by t divided by 1 plus t to the power 2n plus 2, we get 1 plus t to the power 2n plus 4 in the denominator. Every term in the numerator is multiplied by t. We can split this integral into 3 integrals. Each one of them looks like this integral here. That is, it can be expressed in terms of the beta function. From this first term, we get beta of 2. The second argument of the beta function is this power minus the first argument. So it is 2n plus 2. For this term, we have 2n, then beta of 2n plus 1. The second term is 2n plus 4 minus 2n plus 1. That's 3. Finally, we have 2n minus 1, beta of 2n plus 2. The second argument of the beta function is 2. Expressing each beta function in terms of the gamma function, we get gamma of 2n plus 4, which is this power in the denominator. From here, we get gamma of 2, which is 1 times gamma of 2n plus 2. Then we have 2n gamma of 2n plus 1 gamma of 3, which is equal to 2. Then 2n minus 1 gamma of 2n plus 2 gamma of 2, which is 1. Gamma 2n plus 2 is 2n plus 1 factorial. Gamma 2n plus 1 is 2n factorial. Gamma 2n plus 4 is 2n plus 3 factorial, which can be written as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. 2n plus 1 factorial divided by itself, that's 1. And from here, we get 2n minus 1. 2n factorial divided by 2n plus 1 factorial, that's 1 over 2n plus 1. And we have this for n here. 1 minus 1 is 0. We can take 2n as a common factor. We are left with 1 plus 2 over 2n plus 1. This bracket is 2n plus 3 divided by 2n plus 1. These two terms go away. Also these two. We are left with 2n divided by 2n plus 2. That's n over n plus 1. This is the value of the sum of interest as a function of the positive integer n.